Okay, so good evening, everyone. I welcome you all in today's session. In the previous session, Pranav Ahire taught us about neural network, and in today's session, Adarsh Dubey would be teaching us about transformers architecture. So, without wasting any much time, let's welcome Adarsh Dubey on the stage.
Hello, Aryan. Hello, everyone. Thank you for inviting me.
Hello, Adarsh. How are you doing?
Pretty good, pretty good.
Okay, Adarsh. So, before starting, can you introduce yourself to us?
For sure. Hey, everyone. My name is Adarsh Dubey. I'm a third year student. I'm a pre-final year undergrad student. Other than that, I'm also working as a co-developer at We Make Devs, and I'm also a machine learning enthusiast, which is why I'm here. So yeah, that's it about me, I guess.
Okay, Adarsh, we are excited to have you here for today's session. So, Adarsh, you can start with your session.
Yeah, can you please pull up my screen and I'll start. Cool. Yeah. So hey, everyone. Once again. So I don't have any GitHub repository or PPT as such because come on, it's Transformers sessions. So I just need to make sure that I keep doing everything on with my pen. So before we even begin, I think what we should okay, let me just put a timer because the topic is so vast that I might just just go on yapping and don't stop. So I'll just put on the timer. Cool. So before we even begin, let me tell you that this session is for whom, as this is ML Math Club, this session is going to focus on the intuition behind LLMs. So I'm not going to go to any LLM model such as Gemma or anything. Not going to pull up their API key and show you how to build things using LLM. I'm going to show you what happens inside the LLM. Now, when I say what happens inside the LLM, I must say that I'm not really going to focus on the exact core matrix multiplications inside LLM or the exact back propagation algorithm inside the LLM. In yesterday's session, Pranav, I had taught you what is exactly the back propagation algorithm. So you need to understand that back propagation algorithm is, you don't have to write it every time. You can just create an autograd and then you can use it in whatever application you want. So if you have not watched, by the way, definitely check out Andresh Kanpathi's micrograd video. So I'm not going to talk about back propagation either, and I'm not going to talk about exact matrix multiplication because once we are at the stage of transformers, which is right now the epic stage in the world of NLP. When we are here in this stage, we should not really worry about how MLP works. I believe this is something that you should know by your heart right now, to attend this session. So I won't be talking about exact matrix multiplications, how backpropagation algorithm works. Rather, I'll be giving you an intuition on how things flow in the transformers architecture. And when I started learning about transformers architecture, I thought it's just just one architecture that I need to learn. However, over time, I have realized that there are many more things than just having a simple architecture like MLP. So there are so many things that we are going to cover today, and yeah, so the last thing I would like to disclaimer is that there are so many things in the transformers world that I cannot cover everything, right? So I'm not going to talk about fine tuning or anything like that, how LoRa QLoRa works. Definitely worth learning, but not in this session. Other thing is that I'm not going to talk about how every transformers architecture works, because there are like at this point in time there are thousands of architecture, if not hundreds. So explaining all of those would be kind of not sensible for me. What I'm going to talk about is how the original transformers architecture, the one at introduced in Attention Is All You Need, and moving ahead a little bit further and understanding how the generative transformers work. And if you don't understand those words, don't worry, we're going to cover that. But how is this going to happen, right? So I believe enough disclaimers, and I'll start. So the first thing is, we have introduction, which is done. Now prerequisites. So what do you need to know to understand the transformers architecture? It is that first of all, you need to understand what are MLPs, multi-layer perceptrons, and you learned that yesterday, so good with that. You need to understand how RNNs and LSTMs work. So because transformers is generally used in natural language processing, you need to know how an RNNs work, and that's how I'll be able to tell you that why we prefer transformers over RNNs as of today. You need to know how LSTMs work, and you need to know, all the back propagation algorithm for all of these, and what is the intuition behind and everything. For RNNs and LSTMs, it's fine as long as you have, a basic intuition on how feedback neural network works. I can tell you why transformers over RNNs, and you don't need anything else. Other than that, you also need to know in I believe this is enough of the prerequisites, right? If you know all these, then I believe you're good to go. And so I'll start with why transformers over RNNs in the first place. Why do we need transformers? So if you have studied RNNs or LSTMs, which are a type of RNNs, you will understand that they are feedback neural network. And why are they feedback neural network? Because it is needed. We need a neural network which can process sequence. So when we did not have NLP RNNs, we had simple MLBs. So suppose these are our input, these are our first hidden layer, and there's a whole lot of architecture after it, and these are 1 x1 x2 and x3. Then we can enter x1 x2 x3 parallelly in all of these, but the problem with that is we don't really have any sequence processing ability. So if x2 somehow depends upon x1, our neural network will never understand that, because all the three x1 x2 x3 features are going in directly. So you need to understand why MLP fails and why we need RNNs. So why we need RNNs? What are RNNs? RNNs are basically feedback neural networks. So suppose I have a data point X and it goes to a neuron which has some summation and suppose sigmoid function or whatever function, and produces Y. Right now, this will go back to the neuron for the next data point. So if there is X, so it should be Xi and Xi. So for x1, it will be simple calculation, right? I don't need to write all that. But for x2, it will be everything that was supposed to happen with x2 plus y1 hat. Y1 hat, so that we understand that the output of our previous calculation was one of the input in our next calculation, and that's how sequences follows, right? So why one should choose transformers over RNNs when we already have these kind of feedback networks? There are multiple reasons, such as vanishing gradient problem. We have heard about that. We have learned about that. There are some other problems with general activations as such, and not really needed to feedback neural network. But one big problem is that you need to understand that I'll draw a general unroll of RNN. So there is x1, x2, and x3. And all of these have output. And then it goes like this. So this is basically unrolling the recurrent neural network, right? Now you need to understand that to calculate x3, you need to first have y2 hat, and to have y2 hat, you need to go ahead with the computation of x2, and to have that, you need to have the computation of x1. So you need it in sequential manner. You cannot compute all these parallelly. So the major problem with RNNs is that they are computationally very slow, because you cannot use parallel algorithm to solve all this. Now, how transformers are better than RNNs? Because I said this line, we understand that transformers have a fixed length, and all of that goes in the transformers architecture or the language model at once. So all of this, however features they are, all of these goes into the transformer architecture at once. Now you will say, but but it is all about natural language processing, right? How is it possible that all of these are going in parallelly, but they still understand how one word is affecting the other word? And that's the beauty of transformers, because we have created such an architecture that we do not need to rely on sequential input. We can have parallel input, and still we can focus on how one word affects the other word, and how one particular data point affects the other data point. So you need to understand that transformers are better than RNNs because they allow users, or they allow us to have parallel computations. And as you know, we all there's such a huge demand of GPUs, and you need to understand that why is there such a huge demand of GPUs? Because of transformers. Because transformers allow parallel computation, we all need GPUs. We can make do those parallel computations, and we can do them so easily, so fast on GPUs, that we are able to train such huge models. So okay, cool. I believe enough talking about RNNs and dominance in today's time. So whatever model I believe you're using today, 90% of them are now transform models, right? Even even to an extent, you can say that if not transformers, then something that is used in transformers. If you're using YouTube, you will think, but others, where is YouTube using transformer models other than replying, having a chatbot? Where is YouTube using transformer models? So YouTube is not really using transformer models, but there is something. So suppose if this is transformer models, TF. So there is something on top of that which we're going to look at later, embeddings. So if YouTube doesn't use transformers, they use embeddings, which each of the transformers use uh, for a recommendation system. So if you have used YouTube and you have thought about it, if you continuously watch one type of videos, you will get those type of videos in the recommendation as well, right? So that is a recommendation system, and that can be built using embeddings. Anyways, so in today's time, we are 90% of the place are either using transformer architecture or something that is used in the transformer architecture. And why you should learn transformer architecture? So even if you are not really into machine learning, or even if you are not really into this whole mathematics thing, you just want to build something quickly using transformers, I believe having a basic understanding of transformers, how transformer works under the hood, will definitely make give you an edge and help you build better models, help you build better applications and better things with just by using LLMs, right? Because we understand how the internal workings, we know what are the best parameters for us and what is context length and everything. So I'll be explaining all that, and I'm very excited for it. So I believe we are done with introduction, and now I'll move on to the second part where I introduce you what are transformers. So a lot of people think, wait, I'll just have adjust my screen. Cool. Yeah. So a lot of people think that transformers is basically chat GPT, and it's basically how it is basically used in text generation, but it's not the case. Transformers actually have a very wide variety of models. Now what are those models? We are going to look all of this in today's session, but I'll just quickly tell you what are these. So there is this original transformer. I'll just write OGTF, and it has two parts. It has a block called encoder and a block called decoder. Okay, and then we have simple general text. We input that text in the encoder block. The encoder block produces something called as context, and then that context is used in the decoder block, and the decoder block produces generated text. So this is the original transformers architecture, and it was introduced in the very famous 2017 release paper, Attention is All You Need. But this architecture is not in use today for generative models. Then what is in use today? So this model was actually produced, it is named transformer because it was built for the purpose of translation. The original paper, the Attention is All You Need paper, talks about how we can build an architecture which is transformers that can be used to convert, to translate English text into German text. So even though it started as just an architecture which is used for translation, people explored every component of it, and we understood that there is much more to it. And today, be it classification or any kind of thing, for using natural language, or be it text generation using natural language, we are using some part of this particular architecture. So this was actually the paper in Attention is All You Need. This is the original, and it was not generated text, rather it was German text, and this was English text, right? So this is the original Transformers architecture. People explored what if I just use the encoder block of it, because you can see there are two blocks of it, encoder and decoder. People explored what if I just use the encoder block. So then we created something called as encoder models, or encoder only models. Some people might like to say it like that, which has just one block called the, yes, you guessed it right, called the encoder block. What does it do? You need to understand what does this encoder creates. It creates context. It creates text. I'll just mute. Yeah, I'm so sorry. So encoder creates context. I can put in input text and it will output rich context. Now, what is this context? It doesn't create generated text. It creates some numbers. This context is basically array of something, right? So it can be 1, 2, 0.5, 0.1. It creates a context. Now, what is that context? We'll get back to that. But now, okay, so this is the original transform, and this is the encoder only model. And as you might have guessed, people explored encoder only model and they get some really great results. So people wanted to explore naturally decoder only models, and that's how decoder only models were born. So there is this third thing called decoder models or decoder only models. What are these models? So these are simple models which only have the decoder block. They don't have the encoder block. And you might ask, "Ki, ठीक है, Adarsh, everything's fine. I understand that. But according to your definition, the encoder block produces some context which you told us that it is some numbers, and the decoder blocks takes in that context. So the decoder block naturally, intuitionally takes in some numbers. You only explained that the decoder block takes in some numbers, but these decoders block, we don't give it some numbers. By the way, if I have not mentioned, these are the block models which are generative transformer models. So this is the architecture of GPT or anything as such. You can just name any model, maybe DeepSeek. They also at the very bottom, this is the model they are talking about. Okay, so it takes in some numbers, which is the context, and produces some generated text. So now we understand that what does encoder do? Encoder generates some context, and what does decoder do? Decoder takes that context and generates some text. Now, what are the use of these models? So starting with this is the only original translation model. Translation, it was made for translation. These encoder models are also known as representational model. I'll not write representational model, because they don't generate anything, but the output represents something. And what does it represent? It represents number, but on a on a surface level, I can say that it represents whatever task you give. So there might be a case that you want to have a model which classifies thing in good, bad, or neutral. Okay, so we have three classes: good, bad, or neutral. And you all have used all these MLPs to create classification models as such. The problem with those, I'll just quickly go over it. The problem with those is that some sentence like I am not really happy because so and so happened. The problem with MLP is that it sees two words, happy and not, and it then needs to weigh which word is weighed more. In some case, there might be a case where happy will be weighed more, and this sentence will be classified as a positive sentence. But in fact, this is not a positive sentence. It is a negative sentence because it says not happy. Not has an effect on the word happy, right? And that's why we don't use MLP. And then there are RNNs, and then there are these encoder only models. So what these encoder only model will do is that it will create a context of three numbers, which will be the how probable, what is the probability of the sentence being it is happy, being neutral, and being sad, being good, being bad, or being neutral, whatever you can call it. And it creates such a context, so it does not generate any text, but it returns some numbers. And that's why this is known as the representational model, because this model represents text. It can be that it might represent that the text is in good will, or it is in bad will, or it is in neutral will, right? So it represents. Now these are known as generational models. The decoder only models are called as generational models. So generational models, they generate something, they take in the context, and then they generate something, right? And as an example, you can go and ask ChatGPT, hey ChatGPT, teach me something about transformers, and it will return some text to you. So ChatGPT is generating something because it is built on top of generational model, which is a decoder only model. Cool. So to recap this very section, I'll just quickly explain. The original architecture that was introduced was this architecture. It was encoder decoder model, right? So you have an encoder, you have a decoder. Encoder takes in some text, produces some context, and give it to decoder. So it is context here. And decoder takes in that context and generates some text. So this is the encoder decoder model, originally introduced in 2017 in the Attention is All You Need paper. What happens inside the encoder or what happens inside the decoder, we are going to look at that, so don't worry about that, but just have this in mind. What is encoder decoder model? Then we have encoder only models, which are also known as encoder models or representational models. What do these do? They take in some text, and then they produce some output, and that output is generally numbers. We generally call it context. And then there are decoder models. Decoder models, or you can call them generational models. Decoder models take in some context, they take in some number, and then they produce some text. So if it is text to context, it is an encoder or representational model. If it is context to text, it is decoder or generational model. Okay, now you might have this question, but others, these takes in number, but ChatGPT takes in text. What are you even saying? You're saying that ChatGPT is based on decoder only model, is based on generational model, but these models takes in number and ChatGPT takes in text. So that conversion is one of the major part which we are going to look today. Okay, from text to number, we are going to do that manually. And I'll explain you how that works, and it's a very beautiful algorithm. But for now, just understand all these three types of models. Now, before I begin, I just like to emphasize on this one thing about a recent history in language AI. If you folks remember, somewhere between 2018 or 2019, the release of GPT happened, right? In 2017, this paper was released, uh, attention paper, the paper which mentioned attention, right? In 2018, one more modern model was released was BERT model. So after this encoder decoder model, people started exploring what happens when we use encoder only model, and they reached BERT. And when they reached BERT, they were like, okay, if encoder only model gives us something useful, then decoder only model will also give us something useful, and that's how we reached GPT. Okay, simple. Since that day, we are having quite a lot of models, and I'm very happy when I say this. We have a lot of open source models as well, so we understand what are the architectures of those models, and we have some proprietary models as well. We don't understand what happens of those models anyway. So I believe enough talking about the architecture, right? So I'll simply just talk. Anyways, so let's move on to word embeddings. And now, what are word embeddings? So I'll quickly tell you the exact architecture of generational model, not the exact, but an overview architecture. So there is this thing which we are going to explore called as transformer block. Okay. Now on top of that, there is this thing called embeddings, and then there is this thing LM head. So we put in our text. So suppose whatever the text is, suppose it is how are you. This text goes into the embedding layer. Then from the embedding layer, it goes to the transformer layer, and from the transformer layer, it goes to the LM head layer. Okay, cool. We'll look at how the embedding layer works. Then we'll look at how the LM head layer works, and then we'll look at how the actual transformer layer works, and we'll look at the entire flow. So from this point on, we're going to talk more about generational models, because I believe everyone is interested in that, and that's a very interesting topic to talk about. Okay, so what are word embeddings? So right now we are going to look at this. Okay, we are going to look at this. I'll just quickly give the heading. Embeddings. Okay, so we're going to look at embeddings. What are embeddings? Before I talk about embeddings, let me talk about something much simpler. Suppose you need some way of representing words or anything natural language into numbers. There are multiple ways to tokenize them. So what is tokenization? Tokenization is the process of converting words or characters or subwords. You're going to look at that to numbers. This process of converting word to number is tokenization. Cool. So suppose the question is, how are you? Right? So you might just say, okay, I'll start giving a unique ID to each of the words. So if it is how, I'll give it 1, and if it is R, I'll give it 2, and if it is you, I'll give it 3. That way, my token will be 1, 2, 3. This makes sense, right? This makes a lot of sense. You have now converted text to number, and the process is known as tokenization, and the output you get is token. So your token is 1, 2, 3, which is good. But suppose you create a vocabulary of as such. So creating, giving a lot of words their own unique IDs will be creating a vocabulary. You can create a vocabulary, but how big will you create it? Suppose you say that I want to create a vocabulary of top 40,000 words. So you take like 1,000 of novels, you will take 1,000 novels, and you will start creating vocabulary out of it. For each unique word, you will give it some idea. Or let's make this easy for you. You can sort all the words by their frequencies. So suppose in a novel, if the most frequent word is king in 1,000 novels, so suppose all those 1,000 novels are based on some king story, and the most common word in all those novels is kings, and king appeared suppose 973 times, and then there will be some other word, suppose it is queen, it will appear suppose 600 times, and there are a lot of words, and there are also words like the will also appear, the will actually appear more than the king, but in this example, let's just consider it appears 573 times. So you take in 400 search words, 400 top words, words with the most amount of frequency, and you start giving each of them some ID. So you say king is 1, so I'll just write frequency, word, and ID. You say king is 1, queen is 2, some other will be 3, some other will be 4, and that's how there will be 40,000. So now you have created a vocabulary of 40,000 words. But that's not how English works, right? English doesn't just have 40,000 words, it has million words, it has more than a million words. So the thing is, you can create a vocabulary, but you need to create it of 1 million words. Is that even possible? That will require a lot of computation and that will require a lot of time. And will it be worth it? So this is simple word tokenization. Okay. If this is not the answer, then what is the answer? So some people came ahead and say, okay, it's fine. We'll tokenize not the words, but we'll tokenize the characters. So there is A, there is B, C, up to Z, then there is A, B, up to Z, and then there are special characters, suppose, and there are other symbols which are numbers. Numbers are also symbols, right? 0, 1, up to 9, and then there are some special characters such as and, at, hash. Suppose you tokenize all of these, then it will be very limited in number because there is a very limited number of characters we have. As of now, the useful characters are generally 576. Obviously, you can keep adding more on these, but those are used very rarely. So you have to just tokenize 576 character, which sounds beautiful. That I can give A1, B2, this A 27, this B 28, this Z, or like whatever, 24 plus 24, 48, 26 plus 26, 52. Right, you can say, okay, we have given an ID to each character. Now our work is easy. Now suppose someone says how, we'll just do HOW and we'll figure out the IDs of these. So suppose it is 10, 15, and 20, which is wrong, but for suppose, and then the word will be 10, 15, and 20. So this way, I do not need to know all the words in the world. I just need to know all the characters in the world, which is actually less than the number of words. This is really great. But as the research progressed, we understood that this is not the most efficient way. Why? Because now this array has a lot less information about the word how. This array is not actually able to contain the meaning of the word how. Because suppose I create something like how and who, right? So this will have a similar array. This will have, the arrangement will be different, but will have the similar array. So how and who will mean kind of same, which is not the case in every context. In some contexts, how and who might mean something similar, but in other contexts, who and how might mean something completely different. So this kind of array is not able to contain the meaning of all the things. Okay, we are past 32 minutes. I need to move on. So this was not the most efficient way, and then that's how we figured out sub word tokenization. What is sub word tokenization? It is actually how it is tokenized in today's world. So I can say something like, okay, LLM specialization with Adarsh. Okay, suppose this is a sentence and I need to tokenize it. What I'll do is I'll do word tokenization, right? So this will be 1. And suppose my vocabulary doesn't include the word specialization. If that was the case in our first tokenization method, we would have to ignore specialization, right? But in sub-word tokenization, what we do is we simply just tokenize this as to and this has 3. Simple. So now I have a not I will be here. So I have a token for special and I have a token for isation. Because isation is used in a lot of the words, it will be very useful. So this is how tokenization is done today. Creating words and converting them to numbers is what we do today, right? And the algorithm used is BPE. It is one of the most famous algorithm, and then there are other algorithms as well, like word piece. And I'm not going to talk about all of these because there's not a tokenization class. It's a session on transformers, right? But this is how you create words to numbers. So now you understand when I said that we give it some numbers, and you were like, and you might have asked, but others, we give it some text. No, we don't give it text. We give text to ChatGPT, but before giving it to the actual base transformers architecture, base model, it converts those words into numbers. Are those numbers tokenization? No, they are not actually. What are these? Those are embeddings. But before moving on to embeddings, I just want to show that um, GPT tokenizer playground. So you all can go at this and say, yeah. So this is the actual tokenizer of ChatGPT, right? I'll just zoom in a bit, and you can say how language tokenization works. Let's go to GPT-3 for legacy purpose, and whenever I type something, so you can see there are 7 different tokens for these many words for this whole sentence. The first token is hi. The second token is space there. It is not just their word, it is their word, but before their word, there's a space. There's a special token for comma as well. In our implementation, there's a special for comma. Then there is a token for how with this space, R with this space, U with this space, and question mark. So these are tokens, right? And before the text goes to the base model, it is converted into tokens. As simple as that. Now we're done with tokens, but others, you said it's not just tokens, right? It is something else. So you need to understand that tokens don't actually contain meaning. If there's a token for king, and suppose the token is 973, and suppose there's a token for queen, and the token is, let's not consider minus, let's consider it 7542. These tokens are supposed to mean something similar. I'm right? These tokens are supposed to mean something similar, but do they mean something similar? No, they don't, because these numbers doesn't contain any meaning. Now what if I say that there's a word called bad, and there's a word called not, and then there's a word called not bad. Now for this particular example, I'm considering not bad to be one single word. Okay, it is not two different words, it is one single word. I can say ki, okay Adarsh, it has some tokens, so I'll just do current. It has some tokens, and the token for bad is suppose 73. For not this, it can be 955, and for not bad, it can be 72,533. Whatever the token is, I can say ki Adarsh, but if I try to encode the meaning in an array, I can make it. I can create a token based on one property for now, just one property. On does that word mean it is happy or it is sad, it is good or it is positive or it is negative. I can just try to encode its meaning in just one particular number, how much happy it is and how much sad it is. So if you want to see, you can draw a graph like that. You can say this is positive, this is negative, and suppose the word bad is somewhere here, right? So you can say bad is here, and not can be here, and not bad together can be here because it means something positive, not bad. which means good. I can say, Adarsh, the magnitude of bad being bad is minus zero point 0.9, minus zero point 0.7, minus zero point 0.5. Now, this is just me trying to encode all of this manually in one particular dimension. What if I say I need to embed it in 1000 dimensions? So embeddings are basically multi-dimensional encoding of a particular word. So suppose if there's a word like king, it will have an array of around 1600 length. What does that mean? That means that each of the value in the array, which is known as the embedding, that this array is known as the embedding of king. So this array, this embedding of king will have 1600 values, and each value will represent something about king. So if there is a word called queen, now it has the idea of whatever we consider 573, and it might have the idea of 7244. These IDs don't actually correlate, but this particular array will have some similar values than this. The embedding of king will have similar values as the embedding of queen. And when you try to plot vector embeddings on a 2D graph, and if you plot something like cats, so there is cat, there is dog, and there is puppy. So all cats, dogs, and puppies will lie somewhere near the same region, and the king, queen, and whatever the emperor, joker, whatever it is, these all will lie in the same region. So what is embedding? Embedding is basically representing a particular word in multidimensional space. Okay, again, not going a lot in depth because there's so much to learn how this embedding is done. It is the first paper that talked about embedding was Word to Vec. It was about creating embeddings out of tokens. So it takes in tokens and create embeddings out of it. All of these topics I'm talking about, these are not transformers architecture. This is something that you need to know to understand transformers architecture. So we are not going in a lot of depth to understand what is embeddings, but you just need to understand for each word, suppose the word is how, it will have some token which will be arbitrary, which will not have any meaning. And because the tokens don't have any meaning, we need to represent those words in a way which has some meaning. So it will have some ID, but it will also have some embedding. Each word will have a token, and each token will correspond to a particular embedding, and that embedding will contain multiple values, and those values together represent that word in some or the other dimension. So it is not like this, but intuitionally you can say that the third value in the entire embedding is representing how much the word is positive, neutral, or negative. If the third value in the embedding is negative, it means the word is negative. But in some other context, it might mean dog, and negative and dog are not related. These contexts are not related, right? So it can be a negative word and it can be a word related to animal. And to show all those contexts, to show all those meanings, we need an embedding. So this is just embedding, simple embedding. And how is it created? It is created using a multi-layer perceptron. You put in some random values. I'm embedding, you pass it through, and then you have some general neural network. You can learn more about it if you search for Word to Wake paper, and there are a lot of good videos. There's a really good video of Joshua Starmer, StatQuest. You can definitely check that out. We are already at 45 minutes and we have not even started what are transformers. Okay, so there's just one addition in this. These are embeddings in general, and suppose there's an embedding for how, there's an embedding for and there's an embedding for you, and we put this in our model, we put this in our a decoder only model, representational model. So the representational model takes in this is also the context. All of these together are known as the context, which our model needs. So we pass in the context. Okay, so one nuance is that, which is not really important, but I'll just introduce, is that you don't just need embedding. So you can say this is all the embedding, but you'll also encode the position of the word. So you can say 0, 1, and 2. So in the whole array of embedding, you'll prepend it with the position. It's just that. Okay, cool. And sometimes you want to prepend it with the CLS token. I'll not go in depth because it's not really how transformers work. But okay, this is for this is for representational models. You add the token, and I'll not really go in depth. Oh my god. Okay, one last topic before we actually dive into what are transformers is the topic of. I'll create a new page for that. Auto regressive. Okay. So you might have seen that whenever you use ChatGPT or any LLM in general, you don't get answer all by once. You get answer word by word, and that generation can be really fast. So you might think that it is generated several words at a time, but at the back end, it is generating one word at a time, just one word. And this principle is known as auto-regressive. So what do transformers or what do LLM models do in general? Suppose I can say, hey, it was a happy day because, and then I just give this particular sentence, hey, it was a happy day because. And what transformer will do, what the model will do, it will generate the next word. It will predict what can be the next word. So it will predict, suppose it predicts it was a because I, and then I'll give it the entire sentence again from hey to everything in between to because I, and then I'll ask it to predict the next word again. So first it predicted I, and then I asked it, okay, now you predicted I, now predict the next word. So hey, it was a happy day because I, and then I asked it, okay, what can be the next word? Because I was. Now I'll give it the entire sentence again from hey till I was, and I'll ask it predict the next word. You see how we are generating the next word, and we are giving the next word as an input to generate the next word. So this particular principle, this particular technique is auto-regressive. Basically, it regresses over the entire sentence one by one. It generates an output, and then it appends the output to the previous input and gives it as the next input. Okay, how this is how input works. Okay, cool. So now we understand all of this. So this was embeddings, and this was auto-regressive. Let me talk about the actual attention architecture. And I believe the best way. Okay, how do I type? Yeah, you might be in here just for this particular topic of attention. What is attention, right? We have heard so much of attention, but what is it? Okay, I'll start with introducing you with the concept of attention by introducing you the need of attention. Suppose we did everything I talked about. Suppose I created a token vocabulary. So now all my words have a token, but those token doesn't contain any meaning. So we also create embeddings. Suppose with the help of those tokens, we also create proper embeddings. Now what? Now we can give it to the model. Yes. Will it work? Will it work? You need to understand that each word has some meaning, but it will also have some context with respect to the other words. So, for example, the very famous word bank. In one context, it might mean the financial bank we go to, right? The bank we visit, ICC, SBI, not ICC, ICICI. So it might mean bank. Now in some other sentence, it might also mean river bank, which has nothing to do with financial bank, which has nothing to do with SBI. It is the exact same word, but it means river bank now. In some other context, it means river bank. And in some third context, it can also mean the road bank. And by the way, if you don't know what is a road bank, then suppose if this is a road going forward, then you just bank it by some angle, right? So for racetracks, you need to have banked road. Need to have banked road. So the road is now banked at an angle. You might have studied this in physics, right? So bank will also mean SBI, ICCI, ICICI, and river bank, and also road bank. How does our model understand what is the bank? What bank are we talking about? So what is attention? Attention is literally nothing. Attention, the work of attention is just that you give it. So suppose there's a sentence called by the river bank and something next, right? Each will have a embedding. Each word will have an embedding. Cool. Now this is the attention block. Attention is a layer. You can think of attention as a layer. This attention layer takes in all the embeddings. Cool. And it produces 4 more embeddings. Okay. Now, what is special about these new 4 embeddings? It will mutate or modify or make some changes in the original embeddings with the help of the embeddings neighboring those embeddings. So for this particular embedding, there are 3 more neighboring embeddings, right? There are 3 more embeddings which are neighboring this particular embedding. So I'll talk about the bank embedding, right? So this bank embedding also has 3 neighboring embeddings. What attention block will do is that in this particular embedding, which was corresponding to the bank one, it will introduce some amount of context from these 3 embeddings. From these 3 embeddings. So bank, before anything, bank meant bank, and the model did not understand if bank was in the context of SBI, in ICICI, if it is in the context of river bank, or if it was in the context with the road bank. The model did not understand, but attention block infused some meaning with the help of these 3 other contexts. And by and the doesn't really correlate with the word bank. They don't correlate with the word bank, but river does correlate with the word bank, because river bank together means completely different things. So the infusion from the word by and from the word the will be really less, but the infusion by the word river will be very strong. So now this particular embedding, which doesn't mean bank anymore, it means something heavily bank and something heavily river. Okay. So what is attention? Attention is basically a layer which basically takes in some embeddings and produces embeddings of the same length, same number of embeddings of the same length, but it infuses meaning of other embeddings into other embeddings. So this way, a model understands the concept of neighboring embeddings, the concept of neighboring words. What RNN used to do, RNN used to put it in sequentially, right? First, it would put in river, and then it would put in bank. That's why it was working. Why? Because river has been processed already. That's why bank now will have some meaning of river, but it needed sequential input. Transformer fixed it by using the attention block. And what did the attention block do? This is actually the comparison between attention block and RL. What did the attention block do? The attention block basically infused meaning of every embedding into every other embedding. And how does it infuse this? We want to talk about that. But anyways, so this is embedding, and most number of parameters are used here, or there is an other block which we will talk about here. Anyways, so this is attention, and you need to understand this famous word attend. So if you're ever going to read a book or ever going to watch a video on how LLM works and everything, you need to understand what does attend mean. What does attend mean? Attend mean the word river attends to the word bank, because river bank has some special meaning. But the word buy, does it attend to the word bank? No, it does not attend. If a word attends some other word, such as if river attends bank, then the meaning of river will be infused in the embedding of bank. And if the word bank attends the word river, then the embedding of river will somehow be infused in the embedding of bank. Okay. So in general, you will see people drawing such kind of grids by river and bank, and by a river and bank. Simple. And you can say the buy to buy is a full attention, because buy does attend to buy, because it doesn't really matter, right? It's the same word. Buy does it buy attends to river. Does it attend? No. Buy doesn't mean anything related to river. So I can say it is 0.01. It is 0.02 here. Now okay, obviously it will be less here as well. Now does river attends bank? Does river attends bank? Yes, it does attend bank, because river bank means something special. So I can say 0.8. It has a high attention. And using this attention value, we basically infuse the infuse the embedding of attention, infuse the embedding of river into the embedding of bank. As simple as that. Now, the next thing, LM head. What is LM head? So, as I drew previously, this is our generational transform architecture. We have embeddings. We put in some text. So we saw what are embeddings. Embedding is basically vector representational, multi-dimensional representation of a word that contains meaning of the word in different dimensions. It goes to the transformers block, and then it goes to the LM head. Okay, to explain this, I need to go back and talk about one last thing, that is, if there are, suppose, 5 words, and I need, if there are, suppose, 3 words, and I need to generate 4th word out of it. So if there is hey, I am, and I need to generate the next word, it looks something like this. There are 3 embeddings, and I need to generate the 4th embedding. What happens is, and this is the attention block. This is the attention block which does the calculation. What happens is, okay, I'll just take the black. It will pass all these through, but the last one will be a special one, because it will be the answer of what we need. This will be the generated. So the last particular embedding which passes through the attention block will be the answer. So whatever embedding this is, this will be our result, which will be the next word. So suppose it can be 0, 1, 2, 5, 6, And this embedding might mean something like, hello, I am happy. So I can say, okay, okay, the next generated word is happy. How does it know that this particular embedding means happy? So we need LM head for that. So this basically gives us, the transformer block gives us a lot of embeddings. The amount of embeddings we put in, it produces the same amount of embeddings. And then the last embedding is passed to the LM head. And what does the LM head do? LM head basically takes that embedding. And as I said, what does, embeddings are not unique. Embeddings, tokens are unique. Embeddings are not unique. Embeddings are basically representation of token in multidimensional space. So suppose this particular output embedding was 0 0.1 minus 5, 3.2, and a lot other stuff. Okay? So this was the output embedding. It 99% of the time it will have no token corresponding to this. There will be no token in the vocabulary which corresponds to this exact embedding. It's a very rare thing to have a token correspond to this exact embedding. So what the LM head does is it finds out top 10 or top 20 or top 100, however many you want, top 100 words which correspond to this particular embedding. So the words can be happy, glad, sad, I don't know, anything else, any other mood, right? Crying, whatever it is, any other mood. So our LM head will find out top 100 words which correspond to this embedding, and it will also produce a number with those. So suppose it can be 0 0.45, 0 0.25, 0 0.5, no, not 5, 0.05, and the summation of all these numbers will be 1. Simple. So you can think of it as a softmax classifier, and I believe you know softmax because we are learning transformers. Anyways, so this LM head basically gives us all the tokens that can correspond to our output embedding, and then it selects one of those tokens, right? You have heard about the temperature setting in LLMs, right? If you have built anything using LLM, you might have heard about the temperature setting. What is the temperature setting? If the temperature is 0, then it always chooses the first word, the most probable word from the LM head output. But what does that mean? That means it kills the creativity. There will be something very less creative. It will be, very generic text. If it is something around 0 0.2, 0 0.5, something like 0 0.75, then it considers the top 3 or top 4 and it will choose anything at random. So because it chooses anything at random, it has this opportunity of being creative. And when it is 1, it starts giving some nonsensical results because it chooses anything at random. So it does all this computation, taken out the top 10 words that can correspond to our output, and then chooses anything at random. And at many times it can be something nonsensical. Okay. So this LM head, what does LM head do? It basically, if I draw an architecture, it basically, after all the computation, there will be LM head here. After all the computation of embedding to embedding, embedding into embedding, there will be a lot of, just reduce the opacity, there will be a lot of embeddings, but the last embedding will go till the LM head, and then the LM head will choose, and then the LM head will produce top 100 words, and then it will, so there are 100 words, and based on the temperature setting, suppose 0.5, it will choose something at random, but something that is, in first top 10 words, something at random. If the temperature is high, it will choose something at random in the top 100. If this temperature is low, it will always choose the first word. That's why a temperature very high produces nonsensical results, but a temperature very low produces very creative-less results, very dead results. Okay, now we are already 1-3, and now I will talk about the proper flow of the transformers, and this will be the last concept. It will take around 15-20 minutes. Cool. So yeah, let's talk about the flow. Okay, cool. So let's start. We put in some text. It goes to the embedding block. It goes to the embedding block. We are clear. Then it goes to the main tokenize transformer block, and it then goes to the LM head. And you might be wondering, others, you have told us about embedding, you have told us about LM head, but you have not told us about the most important part of transformers, which is the transformer block itself. So now let's talk about the transformer block. What is the transformer block? A transformer block consists of many transformer blocks. So TF1, TF2, TF3. A transformer blocks contains of many transformer blocks. Now, okay, others, we understand that a transformer block contains many transformer blocks. What does each transformer block contain? Okay, let's zoom into this. Okay, so let's talk about TF1, because each TF will be similar. Each transformer block will contain a attention layer and simple MLP layer. Yes. So now this is the most interesting part. You need to understand that in the transformer architecture, in the generational transformer architecture, we have text which goes to embeddings. Embeddings are sent to the transformer block, and the transformer blocks sends the final embedding to LM head, and LM head decides on which particular word to choose as the output. That word is chosen, which is appended to our previous input, which is the auto-regressive part. And now, what is the transformer block? A transformer block contains multiple transformer blocks. And what are multiple transformer blocks? Each transformer block contains an attention layer and an MLP layer. Now, this is the most low level overview you will get. Most low level, okay. And now, what is the attention layer and what is the feed forward? What are MLPs, right? We just learned about this yesterday by Pranav. Very cool. So, what are attention layer? So, let's talk about attention. I have already given you a basic preview of what it does is, but attention layer looks something like this. So this is attention layer. Attention does two things. It does relevance scoring, and it does combining info. Now suppose the attention layer gets 3 embeddings. It will first decide the relevance score for each embedding along with the next embedding. So it will decide if these two embeddings are relevant or not, and it will actually give a score to the relevance. So it can say, okay, these two are not really relevant, so I'll just give them 0.001. Are these two relevant? Okay, these two looks to be very relevant. I'll give them 0.9. And are these two relevant? No, these two don't look relevant, so I'll give them something 0.1. Simple. So what does relevance scoring does? Relevance scoring decides how relevant are how relevant is each embedding with along with the all the other embeddings, right? And then what does the combining info does? Combining info takes in all the embeddings again and the scores as well. So 0.01, 0.9 and 0.2. It takes in all the relevancy scores and then it uses those relevancy score and these embeddings to update the weights of embedding. So it will update the weights of all the embeddings along with the relevancy score. So suppose if the relevancy score is 0.01 of this particular embedding with respect to this particular embedding, so it will update the values of this embedding, but not a lot because it is not really relevant to the next two words. So there is no it because it is not relevant to the next two words, its values don't need to be updated. But if this embedding is very relevant to this embedding, which we can see 0.9, so it will update the values of this particular embedding with respect to this. So it will take a lot of values from this embedding and infuse it in this embeddings. How does it infuse? We have three particular matrices here: q, k, v. Q, k, v. Always remember this query, key and value. So query is used in relevance scoring and key is used in relevance scoring. So these two matrices and how they're used, we're not really going to dive deep into it. But this query matrix and this key matrix, these two are used in relevant scoring. So it makes it makes relevant scoring based on the query and key metrics. And combining info is done with the value metrics. Now it does some matrix multiplication here, and as I said in the starting of this particular session, we are not really going to dive deep into that. You really need to have a good course to understand how all this works. But this is at the very basic of attention layer. It contains two things: relevant scoring and combining scores. And then it outputs what? It outputs the updated embeddings, nothing else. It outputs the updated embeddings. Now if you think of, and then those embeddings go into the MLP layer, and as you know, MLP layer tries to find the MLP layer contains actually the most of the weights are in the MLP layer, and around 60 to 75% of all the weight of the transformer block contains in the MLP layer, and we have already learned about MLP layer. Okay, so at the very basic level, what does transformer block do? It basically has multiple transformer blocks. Each transformer block has an attention layer and an MLP layer, and each attention layer does two things. These are not layers, by the way. Let me just be clear. These are not layers. This is a layer while coding. These are just what these two things do. They do relevance scoring of how relevant one embedding is with other embedding, and then it just basically combines all the info. Okay, cool. So this is what the flow looks like. Okay, cool. Text to embeddings, embeddings to transformer block. What does transformer block do? It has multiple transformer blocks. Each transformer block has an attention layer and an MLP layer. Each attention layer does the relevance scoring, then combining info, infusing meaning of each embedding into other embedding according to the relevancy score with the help of query, key, and value metrics. And at the end, it passes it to the LM head. And what does the LM head do? It simply outputs one particular variable, right? So this was the actual flow. So what you need to remember from here is text, embedding, attention, I can say attention I, MLP I, LM head. Why is back propagation? So all I did till now is explain you the forward propagation layer. Why don't we need back propagation in this? Because we can have our autograd and you can just check that out. Okay, cool. I guess this sounds good. What I'll do now is I'll create this gist. I'll give it the heading of transformers station ever in Nashik, and I'll include all the relevant information you'll need. So for now, let me just create an empty. Okay, transformers station ever in Nashik. And how do I edit? I don't know how do I edit the name. Hmm. Okay, chalo, we'll figure that out later. But this is the link for now, and if Aryan, you can post it in the chat, or I don't know how, but if you can post it in some chat or something, that would be really useful. And I'll just have it on my screen for a little while so you all can see. I mean, so if you, I'll put in all the links here, and that's how we, you can just go and check out all the resources you need. Few resources if you want to continue studying more about LLMs, I'll suggest is the first one and the best one according to me, which I personally prefer, is the first one I personally prefer is the hands on LLMs. The second one is, okay, Anuj posted it. Thank you, Anuj. You have this link now. You can go on it, and I'll update it later. The second thing is there's a deep learning AI course you should check. So they have a really beautiful course on how LLMs work. Um, if there are some comments, then I believe we'll take them at the end. I'm not really able to see comments here, but I believe we'll take them at the end. The third you should check is obviously the actual paper of attention, the 2017 paper. You can find it read easily. It is the most cited paper ever. Cool. So these three resources I personally prefer. I'll put them all in the gist as well. Um, yeah. So I believe we are done. And do we have any comments? I'm not able to see if Anuj or Aryan can help me with that. Okay. Is this used only in MLP or is it used in every ML domain? So here's the thing. Uh, the beautiful part, the not so beautiful part about natural language processing or deep learning in general is that one some architecture from one particular domain doesn't really transfer well into the next domain. So you have seen that there are CNNs, right? But CNNs are not in use to generate text. There are a lot of startups who are working on this, but as of now, they are not really in use to generate text. Why so? Because CNNs were made with the image processing in mind. They're not made with text processing in the mind. So I'll say transformers as of now, as of today, transformers are just used for NLP, but no one knows the future, right? So there can be someone. There are definitely thousands of startups working on this right now who are trying to use the architecture of transformers in image processing or some other domain. But as of now, yeah, transformers are used in NLP. Hmm. Do we have something else? Yes, we have. I'm doing machine learning specialization and deep learning specialization course on Coursera uh, of Android engines. So they are they really good? Yes, these are really good. I have personally done the deep learning specialization course on Coursera, and I have a very good friend who has done the machine learning specialization. Those two are brilliant courses. Just to particular things I like to tell you is that, first of all, make notes. Do not skip making notes. Definitely make notes. And the second thing is, keep practicing on the practice notes that they give. And those two are actually the best thing you can do. So definitely go ahead with the machine learning specialization and deep learning specialization. Hands down, these are the best. What are some real world examples of transformers? So if I was not clear enough, there are three types of transformer, right? There is, first is encoder and decoder. The second one is encoder only, and the third one is decoder only. This is used for translation. It was originally introduced in the Attention Is All You Need paper. Encoder block are representational models as well. Encoder models represent whatever the spelling is, representation, and the general explanation is BERT. And all, T5 and everything, these are all representational only model, which can be used for classification or single shot learning or and stuff like that. And then the decoder only models are also known as generational models, and GPT is the biggest example, and then there is Gemma and all the other models, LLMs we use today. These are all decoder. So these are categories and applications according to each category. So we're good with that. Thank you, Learn with Hassan. Okay, so are we done? I believe we are done. Um, hey Aryan.
Hey Adarsh. Thank you, Adarsh, for this wonderful session. It really helped us gain great insights about it. Okay, so I hope viewers learned something new from this. And viewers, I request you all to stay tuned for the upcoming great sessions. And thank you. We'll end now.
Thank you. Bye bye.
Bye.